Okay, hello everyone. Good morning. Thanks for joining us today. It's my pleasure to introduce Professor David Gelbwaser for our today's seminar. Some chance here if you can. I will say. David is undergrad in physics from the University of Mexico.
Like Alan, like Alan. Alan did in chemistry. I think he did a chemistry, but same university.
Department that he moved to Boston.
Yes.
Sometime he has been a postdoc with Alan schools, in back then at Harvard, and then also an institute postdoc at MIT. And 4 years ago, he moved to the Technion for a position, in the third position. And today we hear about steady-state properties of periodically driven quantum systems. So please, David.
Thank you, Dvira. Thank you so much, and thank you for hosting the invitation. I'm very happy to be here today. Today, I will talk about our last work in properties of steady state of periodically driven quantum system. This was put recently on the archive, and this is a collaboration with Milan Sindelka, who is right now in GT, IIT, China. So let me begin telling you a little bit of what I'm not going to talk today, some of my other interests and the research of my group. We are a theoretical group working on open quantum systems and thermodynamics. Some of the areas we work are to trying to find difference between thermodynamics at the quantum and classical level. One nice result that we had some years ago, that heat machines, engines, classically you cannot do it with incompressible working fluids. Quantum mechanics, you can do it because you have energy quantization. So this is just one difference, and we are exploring further differences. Other area is regarding open quantum systems, specifically strong coupling regime. Specifically non-equilibrium devices, you have flows of energies when you have gradients of temperatures, gradients of chemical potentials. And there is an interesting phenomena that I have been discussing for a time with Dvira that is called the turnover effect. The heat flow as function of the coupling strength goes up, gets to a maximum, and goes down at that very strong coupling in general disappears, even though you are interacting very strongly with the bads. Other area of research is regarding what I call thermodynamic anomalies. Maybe this sounds very good with global warming, no? It's a good selling point. Anyway, these are effects that thermodynamic effects that you don't expect. For example, sometimes you want to cool down a molecule, you have to heat the surroundings. That this is not intuitively. Another effect is regarding Wave effect, that sometimes things that are hotter freeze faster than colder things. Another thermodynamic anomalies. And a fourth area of research is regarding Casimir heat engines and thermodynamics of non-reciprocal systems. Some years ago, we find out that if you put two cylinders at different temperatures, and one is made of a type of material that is called non-reciprocal, one of the cylinders will start rotating, even though they are not touching. And this has important implications because in nano engines, one of the big problems is friction. If they don't touch, you don't have friction. But I will not talk about these things today, but if someone has questions or want to talk further, just send me an email. We can do a Zoom. I will be also today later in the university. So, but for today, steady state properties of periodically driven quantum systems. So let's start with some basic motivation. Very simple. I have a non-degenerate n-level system, non-degenerate for simplicity. I couple to a thermal bath, wait enough time. The distribution of the populations of the energy levels will be a thermal distribution. And one consequence, for example, is that you don't have heat flow between the system and the bath. This is maybe a trivial example. But imagine that for some reason you want to change this property, this steady property of not having heat flow. One option is you can drive your system. You put a time dependence in your Hamiltonian, a periodic time dependence. Now, the steady state is no longer a thermal steady state, or doesn't need to be a thermal steady state. And you have an exchange of heat flow between your system and your baths. This example is trivial, but the main idea that I want to put is that sometimes we have some setup that do not have the properties we want. What do? You drive it periodically, get a new steady state, and then have new properties. And this has been used in many areas for many different applications, for open systems and for closed systems. Just to mention a very short list of examples, people have used this idea of periodically driving a system to suppress tunneling in Bose-Einstein condensates. In semiconductors, people have used this to induce topological states. In lattices to create topological and quantum spin Hall insulators. In spin half particles to reduce the coherence. And the list goes on and goes on and goes on. This is a very big area of research called a Floquete engineer, where the basic idea is you drive periodically your system, get a new steady state, and have new steady properties. Now, the steady properties will depend on your steady state, but in general, it's very hard to know what will be, if I put a specific driving, what will be the steady state. And you want to know the steady state because you want to have a specific enhancement of a specific property, okay? Now, if for the thermal case, when you don't have driving, we know that the distribution of populations is just a Boltzmann distribution, but we are no longer in general in a thermal state, so it's very hard to know. This is a very complex problem. That said, people have worked a lot to get some information of this steady state. Sometimes they call it non-equilibrium steady state. In some cases, doing some approximations. For example, of course, if you have weak driving, you can do some kind of perturbation. People have managed, in the case of high frequency driving, to also get some information about the steady state. People putting some restrictions on the Hamiltonian, either the system bad interaction, or the type of driving. Yes?
The question, is it only at finite temperature that's hard to find a steady state, like Brown's steady state would be easily defined, or no?
At any temperature, and even for closed systems, it could be complicated to have the steady state. As a general problem, no? Of course, you have a small system, maybe you can get, but as a general problem, it's hard. And in some cases, closed system and open system, people have managed doing some kind of approximation. And again, I'm citing here some papers, but this is a big area of research. This is a very small example. Papers, but in general, people need to do some approximation regarding the driving, high frequency, weak driving, a specific type of driving. And the question I will talk today is if it's possible to relax these approximations to say something to any type of driving, not requiring any restriction, not high frequency, no specific driving, and get some information of the steady state. And of course, if I ask the question, the answer is yes. But besides the answer, if it's yes, I think how we do it is important, because I think we found some interesting connections between areas that I thought were not related. So let me tell you about the setup I will consider. Again, non-degenerate level system. We will allow to have some periodic driving where the frequency of the driving here is omega, and we let the system interact also with a thermal bath. In our case, we choose a particular type of thermal bath, and in a second we will clear why. It's a free particle gas at thermal state, inverse temperature beta, and we assume low density. The density of this gas is very low. Why we do that? The reason is the following. If you have a low density gas, every time the gas So this will be a scattering framework. The particles of the gas will be scattered by our quantum system. So every time that there is a scattering event, it's a single particle of the gas because density is low. And after the particle is scattered, it goes away and never, never, never finds another particle of the gas. What does that mean? There is no memory. Every interaction is independent. There are no memory effects. You can get what is called a Markovian equation of the evolution of the system under the influence of the gas. This will be the low density limit Lindblad equation or a GKSL equation. And again, as I mentioned, this goes in the framework of scattering theory. Now, the nice thing of having a Lindblad equation is that many of the nice properties of the Lindblad equations can be used. In particular, populations and coherences decouple for non-degenerate level system. So we can now focus just on what happened on the populations of the energy levels of systems. We will forget about coherences, they decay to zero, will not be relevant for this talk. And the population will follow a very simple Pauli rate equation, where these p's are the populations of the states, and AKJ is the transition rate from state K to state J. Now, we are interested in the steady state. How we find the steady state? We put 0 to this equation, and then we solve this. This is a set of coupled linear equations. We can find the steady state. And I did it for you for the first non-trivial case, that is a 3-level system. You get that this is the steady state for a 3-level system. The important thing is that here we have a function of the rates. If you know the rates, you know the steady state. Now, what will be exactly this expression will depend on what we are talking about. If we are coupled with a single butt, if we drive, we don't drive. But the thing is that these transition rates are not independent of each other, and the dependence depends on the physical realization. And the relations between them will be very important to determine the steady state, and we will study these relations. Now, if we are doing a periodic driving, we do what is called a Floquet expansion of the dynamics. And basically, the transition rates for each transition will be a linear combination of infinite transition rates. That here we have this index nu that represents the number of excitations that you exchange with your driving field. And just to show you a little bit about the expression, so these transition rates, one can calculate from a microscopic model. This means from the Hamiltonian. And basically, I didn't want to enter to all the details of the expression, but they depend on the T matrix that one can calculate using a scattering theory. So if the message that if you know the T matrix, you know the transition rates. And now starts the interesting part, is because we know that the whole dynamic system plus the gas is unitary. It's a system plus gas is a closed system. Scattering is unitary. The S matrix has the unitarity property, that is just this simple property. This and the S matrix is related with the T matrix. This unitarity property puts some constraints to the T matrix, okay? So there are some constraints that you can derive from this unitarity. They are called optical theorem. And now, if we constrain the T matrix, this will put constraints on the transition rates. But we said that the steady state is just a function of the transition rates. So if there are restrictions on the transition rates, we will have restrictions on the steady state. So just to summarize this idea, there are many mathematical derivations, but we started from unitarity of the whole dynamics of quantum mechanics. We got to restrictions of the steady state of the reduced system. Okay, so now let me show you how these restrictions look like. The restrictions, I will call them complex balance restrictions, will become clear in a few slides. Look like this, and let me just, these are many equations, so this is for every j. So there are n restrictions for an n-level system. And notice that basically you are relating the rate kj, the sums, with the jk, with the opposite. So this relates, let's say, forward with backward processes. Now we have some Boltzmann factors, and we have a bracket, this bracket that has this expression that is related to the transition rates in the Floquet expansion. And let me call it the bracket, because I didn't find a better name. So if you have any suggestion, please let me know. So for this talk, I will call it the bracket, okay? So what is the bracket? It has a very nice physical interpretation besides the mathematics and will be very relevant, but give me some slides to get to there to build the story of what's the physical interpretation of the bracket. So now let's understand the meaning of restrictions on the rate. I will start from the easy case, the non-driven, and even something more simple than the complex balance that I show. And then I will go to the driven case. So non-driven systems, we consider a non-driven system coupled to a single thermal bath. And someone can tell me what's the most common restriction between transition rates? Wow, you already saw my talk? Detail balance. So this is the most simple. Basically, the restriction tells you that the rate kj and the opposite rate has to follow, the rate of rates follows some kind of Boltzmann distribution. This is very common, and in many cases, this is the restriction that you find. This is not imposed, by the way. You can derive this restriction from microscopic models. And what's the meaning of this restriction? So it's better to go to the steady state. So in steady state, populations do not change. So the meaning of this, the physical meaning of this restriction is the following. Consider a three-level system and focus on a couple of states. And there will be, even in steady state, there is some probability to go from state 1 to 2, represented here by the blue arrow, and some probability to go to 2 to 1. Basically, these restrictions, detail balance, what tells you is that these probabilities are perfectly balanced, are the same to go from 1 to 2 and 2 to 1. That's why it's detail balance. And this applies for each pair of transitions. So if you apply for each pair of transitions, populations of the states do not change. You are in a steady state, and has many other interesting implications. But if you think about it, it's not the only way to get to a steady state. You can do something a little bit more complicated, and it's the following. Suppose you are in state 1, now count the probability flow to all the other states, to 2 and to 3, so these two blue arrows. And if you want the probability of state 1 not to change, you need this to be balanced by the probability flow into the state 1, so 3 to 1 and 2 to 1. And this is what is called complex balancing. So now we have that all the probability out is equal to the all the probability in. If you do this for all the states, then basically you get a steady state. So this is the difference between detail balance and complex balance. The restriction I show is complex balance. And the important thing is that not every system or not every open quantum dynamics keeps detail balance. We studied this 2 years ago. I will not enter into many details, but here I give you a reference. And some of the conditions that you need to violate detail balance in open quantum dynamics is, one, you have to go beyond the weak coupling limit. Second, you need something that breaks micro-reversibility. This is something that is a velocity force dependent, such as a magnetic field, Coriolis force, etc. And you need these two conditions. And this is the reason why detail balance is so common, because most of the works, people assume we couple limits, so you get to detail balance. And when they don't, in general, they don't consider also magnetic fields. So that's why detail balance is so common, but not always happens. So let's see what are the consequences of for a non-driven case of the complex balance restrictions. Again, consider non-driven system coupled to a single bath. And I will show in a few slides that the bracket in the case of a non-driven goes to 1. We assume detail balance is violated. And the complex balance restriction now simplifies, because the bracket is 1, to this nice expression. And one can show that if you consider this restriction between the rates, then the steady state is a thermal state. This is trivial, but this is a consistency check because we are in a non-driven case, okay? So what's the meaning? Take this complicated restriction expression that I show you about the steady state, put this complex balance restriction for the non-driven case. And if you do a little bit of algebra, then basically you will get that these expressions just simplify to the thermal distribution. Now, let me summarize, just not to miss the impact of what I think we did. We started from a system that is not driven, interacting with a bath. We know that the total evolution system plus bath is unitary. And from there, we derive that because the total evolution is unitary, we get that the system thermalizes. Of course, if the bath is thermal. And I think this is an interesting connection because I never expected that thermalization that is related to increasing the entropy of the system, etc., somehow behind the scene is connected to unitarity, that is the thing farthest away from thermalization of the whole dynamics. I think this is an interesting connection that we should further explore to understand, because also can tell you about thermalizations in closed systems. So this is the non-driven case. Let's go to the driven system. Again, now I consider a driven system coupled to a thermal bath. These are the restrictions that we get. Let me take the steady state equation, and I will put those restrictions inside this Pauli rate equation, not Pauli rate equation, steady state equation. We get a new set of equations that look like this. And let's try to understand the meaning of these equations. So if you think about it, this equation tells us the physical meaning of the bracket. Suppose that the bracket, so the bracket has indexes, so there are many brackets. Suppose that all the brackets are 1. The solution of this equation is that the steady state is a thermal state. Okay? Of these equations. So then we transform the problem of finding the steady state to see when the bracket is 1. If it's 1, we know that the steady state is thermal. And now I will analyze the simple cases where this bracket is 1. So I remind you the expression for the bracket is this rate of transition rate. Suppose you have a non-driven system. Non-driven system, basically, all the transition rates with nu different from 0 are 0. Then this sum only has 1 term. This sum has only 1 term. We get the bracket is 1. We already knew that, but it's a good consistency check. But there is another very simple case where this bracket is 1, and this is infinite temperature. If beta is equal to 0, then this exponential term falls down, is 1. And then we recover that the bracket is 1. This means that the steady state is thermal for infinite temperatures independently of the driving. I didn't assume anything about the frequency of the driving. I didn't assume anything about if it's a sigma X, sigma Z, Hamiltonian, etc. of the driving. Didn't assume about the strength of the driving. Infinite temperature, never be at infinite temperature. It's too hot, and also you will not be able to drive your system outside the thermal state. Other way to derive this, and now I will derive it from the restriction, the complex balance restrictions, is take the equation, put beta equal to 0. What you get is that the sum of the transition rates in one direction is equal to the sum of the transition rates in other direction. This is very symmetric. If you replace this in the Pauli rate equation, the Pauli rate equation becomes very, very simple, and the only solution is that these probabilities are the same. This is exactly the thermal steady state at infinite temperature, where you have your distribution is proportional to the identity. So, result, to summarize this, infinite temperature for any driving, your steady state is thermal.
So we are still the dilute. Yeah.
We are in the diluted limit. Will be interesting to check this beyond this limit, if this is general or this is a characteristic of this limit. Now, infinite temperature, we never like infinites, unless it's infinite happiness or something like that. This could be an artifact of the limit. So the question is, yes?
It's possible to interpret this because of infinite temperature, you have like a completely mixed state. And so any kind of drive, the populations are always the same in any possible pair of states.
Yes. But before I did the calculation, I will assume that if you have some strength, if you put a infinite strength driving, maybe you can do. It seems that don't. Although one should be careful with many infinite limits. So, but the question is, okay, infinites are infinite, so sometimes could be non-physical. So what else can we say? And for this, I need to use that at infinite temperature, I'm in a thermal state. If I'm in a thermal state, I don't change on average any energy, not with the bath and not with the driving. Nothing happen on average, okay? So how you calculate the average energy exchange with the driving? Let's analyze all the processes. Basically, consider the following process. You have a process where your system goes from state K to J, and now your driving field is it's a periodic driving. I can model it as an harmonic oscillator. You reduce new excitations of your driving. So what's the probability, or what's the rate of this process? The rate of this process is given by this transition rate. So you went from K to J and then exchange new excitations. The number of excitations is new. And each excitation you exchange has energy h bar omega, okay? So basically, in this specific process, the total energy that you exchange is given by the product of these three quantities. And now, if we want to know all the energy you are exchanging with the driving, you need to sum over all the possible transitions of your system and also all the possible number of excitations you exchange. And now we are interested on the energy exchange at temperature at beta equal to 0. So the transition rate is dependent of the temperature. So basically, we get this expression. Now, we didn't impose this condition. We can derive this quantity from microscopic level. We do some Taylor expansion on the transition rates, and from the model, we arrive that this condition holds. So this basically means at infinite temperature, you're in a thermal state, you don't exchange energy with the driving, everything consistent, okay? Let me just show you some simulations. So here, I'm plotting the transition, one of the transition rates for different nus. Purple as function of beta. So here is infinite temperature, beta equal to 0. Purple is nu is 0. The green one's nu plus minus 1, blue plus minus 2, yellow plus minus 3. Dash are negative nus and continuous lines are positive nus. And you see that the transition rates, when you go to beta equal to 0, go into pairs. The positive and negative go close to each other. Let me zoom a little bit to show you more detailed plot. So basically, at beta equal to 0, you have this relation. One can derive analytically also this interesting relation between the transition rates. And of course, if you have this relation and you plug it in this equation, you get that this is there. Great, it's an interesting properties, but what are the implications of this? And for this, let me get again our steady state equation. And let's do a Taylor expansion on beta. So basically, I need to do a Taylor expansion of this, of this, of this, of this. I will have 0 order, 0 first order, second order, put everything together. I will define we know that at beta equal to 0, this rate has to be 1. And let me define here the first correction. Let me call it PJK1, and I put the beta outside. So this is just the thermal. And then we do the Taylor expansion, put everything there, separate 0 order and first order, second order. We can get an equation for this, the first correction to the steady state. And is the following. We have two terms, difference of energies. And this second term, does it remind you something, this second term? This is basically proportional to the energy exchange with the driving field at infinite temperature. Look, here we have beta equal to 0. We say this term is 0. So the fact that the system doesn't exchange energy with the driving at infinite temperature influence the first order correction of the steady state and give us that the first order correction is just the difference of energies of the levels. But this reminds us, yes?
Yes, maybe I missed it last week. We said that AJK, beta equals 0 equals AJK minus 2, right?
Yes.
And this means that AJK 1 equals, I mean, and we are seeing a number that is important to us. It's just an index.
Yes.
Okay, it's not the power.
Yes,
Okay,
yes,
sorry.
yes. This is an index. Yes. Okay.
You know.
Should put parentheses. It's not the best notation. Thank you. But going back to this, what is this? This is exactly the first order correction of the thermal state. It's function of the temperature. If you expand the Boltzmann factor with the difference of energy, this is the first order correction. So what does that mean? This means that the steady state of the system up to second order in beta is equal or is equal to the thermal state up to second order in beta. I'm showing here some simulations. These are the populations for a 3-level system. Continuous lines are the populations. The dashed lines are the Boltzmann factor as function of the temperature. We see that when beta goes to 0, these come together. Now, again, I haven't done any assumption regarding the driving. Sorry.
as mentioned, is the resultant product function. So basically, they argue that for local Hamiltonians, if the temperature is high enough, then the thermostability design is can be well associated by product state.
Okay.
So I wonder if it has some relation here. For example, maybe the here is also like something to the product state, so it will be robust to the drive.
So I don't know, but I will happy to read to know more about that result, read the reference. So basically, this result tells you that if no matter how strong you drive a system, if you are in a high enough, and here the key words are high enough, the steady state is thermal. Any frequency, any of the driving, any strength of the driving, any type of driving. Of course, the high enough will be related to the strength of the driving, but suppose you have an experiment and you have a maximum driving that you can get, don't be in a too high temperature because you will not be able to drive out your system from a thermostat. So what is high enough? To see it, we can go to our Taylor expansion of this steady state equation. Assume that the first order correction is much larger than the second order. And then we get some equation that for the beta, if the beta is smaller than this quantity, then you are in a thermal steady state. Notice here that again, the bracket, where all the dependence on the driving enters in this equation, second derivative of the bracket at beta equal to 0. Now we plot this quantity. So, and again, here we have indexes. So we have many of these temperatures that tell you when the approximation is okay. So we did it for a 3-level system. We choose a very simple driving. So we assume that the state 3 and 1 can be driven in a periodic way. The state 2 doesn't change. And then plot these betas as function of the driving strength. We see that the betas, of course, when the driving strength is weaker, they're higher. So all this area you are in the case of a thermal state. The interesting thing in this case, and this is just preliminary results, is that it seems, and we need to confirm, to saturate. This means that hopefully, we need to expand this plot, but if doesn't matter how strong you drive, then you will still have a thermal state. For this specific type of driving, it will be interesting to see what happened with other types of driving. I guess this is not universal. I guess that for other drivings, things will not saturate, but this is something to check. Now, we talk up to now about the high temperature limit, but let's see the low temperature limit. We see here that the steady state doesn't correspond with the thermal state. This is not surprising because you are driving, but let's see what we can say analytically. And for this, I remind you some of the expressions we use. The transition rates is a combination of these flocked transition rates, and the flocked transition rates depends on the T matrix. And I didn't mention a lot about the physical interpretation of this T matrix. The square norm of the T matrix tells you the probability of a process. In this case, is the following process. Assume that initially your system is in state J, and you have an incoming particle with momentum P. So this is this side of the equation. And then the square norm tells you that if you are initially this, gives you the probability that the final state of the system is K. You have an outgoing particle with momentum P tag, and you exchange new excitation with your driving field. So this is the physical meaning of the square norm of the T matrix. And now, at beta equal to infinity, the bath is at 0 temperature. This means that the bath doesn't have any energy. Its particles do not have any momentum. The momentum here is zero, basically. So we only need to consider this. In the question, this thing entered here that I didn't enter for simplicity in all the details. But the idea is that incoming particle doesn't have momentum, okay? Here, we consider only process that conserve energy. Initial energy, if the momentum is zero, is just the energy of the system, state J. Final energy, you have state K. You have the energy that you exchange with the driving and the momentum of the outgoing particle. We can reshuffle this equation and then get a nice inequality. Square of the momentum is positive. This basically implies that this expression has to be positive. So what are the implications of this? Let's start very, very, very simple. No driving, nu equal to 0. Basically, this equation tells us that the initial energy of the system has to be larger than the final energy of the system. This is natural because if you are at zero temperature, you only have processes that lower the energy of the system. No? All the transition rates to go up in energy have to be 0. Basically, you don't have this kind of process. And if you have only transition rates going down and everything is connected, then all the population will go down, 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 down. Steady state is all the population in the ground state. That's what we expected. Now, what happens in the driven case? In the driven case, besides the energy exchange with the system, we need to consider the energy exchange with the driving. And even though there are processes that you go up in energy in the system, you can have an energy down on the driving in a way that the sum of energy exchange, the energy exchange driving plus system is still going down. And this you can always do because the energy exchange of the system is finite. And in the driving, you can have infinite excitation, so you can always go down as much as you want. Basically, this means that for any transition, so for any K and J, you can always find some new zero, such as the energy exchange here is much larger than here, and this will mean that this transition rate is not 0, because the transition rates are the sum of the Floquet transition rates. Basically, this means that for every J and K, the transition rate is not 0. And if you put this in the Pauli rate equations, basically, this means that the steady state, that the ground population of the steady state is different from 1. This means that you are not in a thermal steady state. And again, this is for any driving, any frequency, any driving strength, any Hamiltonian, etc. So just to summarize, we started from the fact that quantum mechanics is unitary, scattering is unitary. This allows to derive restrictions on the transition rates, and these restrictions are more general than detailed balance and apply also for driven systems. And these restrictions basically give you restrictions on the steady state. And what are these restrictions? At high temperatures, independently of the driving, with all the caveats that I did during the talk, but if you have high enough temperatures, the steady state is always thermal. So if you want your system to deviate from thermal steady state, never be too hot. And at low temperatures, the steady state for periodic driven system, the steady state is never thermal, it's the opposite behavior. And with this, let me thank Milan, my collaborator, funding agencies, and thank you for your attention.
Thank you. And try to overtake.
Thank you.
So now, questions, please?
So if I understand correctly, you got a time dependent driving field at a steady state. So where's the time disappearance from the collisions?
It's on average, you can cross, you get to a periodic cycle of your system, and you can average over a cycle, basically.
So you're
Yes, you are not taking in the short time dynamics, you are cross grinding. Yes.
that person,
Sorry?
doesn't that hurt? the
I don't think so, but it's something to, the whole dynamics is unitary all the times, no? So you can average, but it's a point to check.
Regarding your conclusion, I expect that when you go at high temperature, I prefer this that when you go at high temperature, you have thermal state because you have, something that, so. For instance, if you also think in many bounding systems, when you go at high temperature, you don't have any. So, for instance, if you consider the temperature policies. Yeah, I mean, you expect that you have thermal state, at least you don't have symptoms, right?
Yes, I personally was not aware that, if for any driving strain, you will not be able to do it.
Okay,
but
so because in this case, it's three-phase drive elements.
yes,
And when you drive, yes, you're introducing something that you expect that people do, not bring you at the thermal state, right?
yes,
Okay. And then instead of the low temperature, you don't have that sheet of thermal state because you have that your driving system is not compensated by the temperature noise, and so you reach negative thermal state.
yes,
Okay. Okay, now so the key is that it's clear.
yes.
Thank you so much for that.
So what is the relation, and so yeah, there are efforts indeed to engineer the phases in materials. And so they drive the material.
Yes.
So if you're driving, so can you get something more quantitative regarding what temperatures? You are constrained to go below. It's part of the challenge over there is that as you drive, you have to hit the material. And then the message that you give us is that then you are losing the phases that you wanted to reach.
Yes, okay, if all these calculations, you assume that, your butt doesn't change temperature, so this will be like another order correction. The temperature that you want to be is this inequality. To be, okay, if this inequality holds, then your steady state is 10. So you should be.
So you're assuming that the driving does not change the spectrum of your system, or these are the altitude.
Yeah, yes. You assume that the bad doesn't change. It's another correction that it could be interesting to see how to introduce and consider. Now, if you hit based on this argument, if you hit your butt, then you will be in a worst situation, no? Because you are higher temperature, and then you will be closer to a thermal state.
This inequality, so looking on the right, depends on J and K, so is it like for all J and K or?
Yes, this is, yes.
Okay. And another question, so do you think it would be interesting to expand those probabilities in higher order in beta and like see how those first non-zero contributions away from thermal state look like? Because one could imagine that then you could like see how to maintain thermalization just to make those higher order zeros.
Yes. Yes, I think this could be a interesting next step, see how far away, depending on driving, so depending on many parameters.
Do you think that this, because you use high enough, right? So it's like, well, my question is like, do you see a way it could sort of expand the regional temperatures where you could thermalize a lot, or it would be just like, it would be still very dependent on driving force? which would like kind of,
I don't know, but this is, I think, like, see how different types of driving affect these temperatures, and if they saturate, they don't saturate, I think this could be an interesting next step to check.
what happens if the drive is associated with some entropy or temperature? Because here you're assuming that the drive is purely classical, it doesn't have any.
Yes, I don't know. Good question, but it's
Last question? If not, thank you very much.
thank you.
Persuasion. Your piece about it's only local basis.
Yes,
So these are the coefficients.
of the Fokker, yes.
So it's just.